Hey guys, Miss Gosling here. In this video, we're going to talk about some of the fluctuations in the cosmic microwave background. So as you recall, in our introduction to the cosmic microwave background, we described the CMB as isotropic. In this video, we're actually going to discover and discuss some of the anisotropies within the CMB. That is to say, some of the tiny fluctuations that we see in the cosmic microwave background. So let's go ahead and get started. So you can see here your understandings, applications, and skills. Feel free to pause the video and take a moment to write these down. These are the things that when you are studying for your test, you should be able to check off to say that you can do each of these things. One thing I want to point out, you'll notice that this application and skill mentions describing. Luckily for you, we are only talking about qualitative descriptions, not quantitative descriptions for the anisotropies in the CMB. So let's go ahead and start by talking about what these anisotropies are. So an anisotropy is a property of being directionally dependent, and in fact is the antonym of the word isotropy and so something that is anisotropic is the opposite of something that is isotropic. And these are both, and isotropic is a term that we have used before, so hopefully you're a bit familiar with it. So the temperature of the CMB is almost uniformly 2.7 Kelvin, approximately. But there are tiny variations in that on the order of 10 to the negative fifth Kelvin. So they're extremely small, but they are measurable. And those measurable anisotropies come from quantum fluctuations in the early universe that have since expanded, and from density perturbations, which is another word for disturbances, in the early universe. So essentially, they come from quantum fluctuations, so things that are moving in unexpected ways in the early universe, and from slight disturbances in the density of the early universe. Okay, so great. There's these tiny differences in temperature in the cosmic microwave background. Who cares? Hopefully, you care, because the anisotropies in the cosmic microwave background explain the formation of galaxies. Because what happens is those anisotropies mean that there were some parts of the universe that were slightly hotter, slightly denser than other parts of the universe. Those hot, dense parts of the early universe drew together due to gravitational attraction. And so what happens is the hotter and denser parts of the universe get even more hot and even more dense as they pull matter nearby towards themselves. And so eventually, those areas will become dense enough to form planets and stars, galaxies, galactic clusters, and most importantly, of course, you and me. So it is in fact thanks to the anisotropies, those little tiny 10 to the negative fifth Kelvin differences in the cosmic microwave background that we exist at all. So, okay, we know what it is. We know what anisotropies in the Big Bang are. We've learned a new vocab word, anisotropy. You can impress people at parties by using that word. We have learned about why they exist. We learned about what they mean for us. But as with any scientific theory, it's really important to know, where does this data come from? So this data comes from three key experiments. There's COBE, which is a NASA satellite that measures the CMB and discovered that the cosmic microwave background has near-perfect blackbody radiation spectrum with very faint anisotropies. There's the WMAP experiment, which created the oval map of the CMB that I've shown in all of these slideshows. And it shows the temperature differentials in the CMB, which are signified by color. As you would expect, red places are hotter than average and blue areas are colder than average. And then finally, there's the Planck Space Observatory, which mapped the anisotropies in the CMB to a high level of resolution and measured the average densities of ordinary versus dark matter, which is super fun, and we're not going to get into that yet. So let's go ahead and take a look at an example. The cosmic microwave background, CMB radiation, is observed to have anisotropies. A, state the nature of the anisotropies observed in the CMB radiation, and B, identify two possible causes of the anisotropies in A. So take a moment, pause the video, and see if you can answer the questions on your own. When you have answered them, go ahead and restart the video and rejoin me while we discuss the mark scheme for this question. So for part A, you're essentially just defining what the anisotropies in the cosmic microwave background are. So that is to say, you should be saying that either the temperature or the peak wavelength or intensity of the CMB varies or is not constant in different directions. A couple of things you'll notice here, we have some backslashes. These are showing different options for the ways that you could phrase things. The other thing you'll notice is that there are these little triangular brackets around some of the phrases. Those are words that are optional, but might be commonly put in the explanation. So go take a moment, make sure you said the temperature or the peak wavelength or the peak intensity of, let me back up. Bare minimum of what you should have said here is the temperature varies, and that is it. That's all you needed to say. Or you could say wavelength varies or intensity varies. If you added more details, like mentioning the CMB or mentioning that as a very slight variation, that's great, but you actually didn't need to say that. So just a fun thing to know with these state questions. Often you can answer them in 5 words or fewer. So that's part A. For part B, you hopefully went back to your notes from an earlier slide and just copied down the answer, right? Quantum fluctuations or density perturbations. That is it. You should have both of those things to get 2 out of 2 marks. So with that, that brings us to our takeaways. So first, there are small fluctuations in the CMB, which we call anisotropies. And the key thing that we have talked about is that those anisotropies have a different temperature than the rest of the CMB. Second, the anisotropies in the CMB map to the locations of galaxies and other massive astronomical phenomena. And so they are an explanation of why there is a Milky Way galaxy here and not a Milky Way galaxy 3 light years to the left. So with that, you have learned all about some of the differences in the CMB that have led to the universe looking the way it does. So there you have it, guys. That is the introduction to the anisotropies in the cosmic microwave background.